So again, just as a quick refresher, specific heat, okay, is essentially so specific heat is going to be the amount of heat required to raise the temperature of a substance 1 degree, to raise the temperature of 1 gram of a substance, 1 degree Celsius. Okay, so just a quick refresher on what specific heat is. All right. So we have that. Now, I'm going to show you guys a couple of these different equations that you can use. And so this one is going to be the equation for essentially calculating heat. Okay, and it looks like this. You have Q equals, I'll extend this out. Okay, Q equals C times M times, and I don't know how to really do this because there's not a, I wonder if they have up here a little, nope. And so this would normally be a triangle, a delta sign is what it shows. So I'll just go ahead and type in delta, and in parentheses I'll put triangle, okay? T, all right? So this equation is Q equals C times M times delta T, all right? Q in this is represented, Q is heat absorbed or released in an equation, or in a reaction, okay? C is going to represent the specific heat of a substance. Okay, and this is generally in the unit. The unit is joules per grams times degrees Celsius. Okay, and this is grams. So joules per grams times Celsius is generally what you'll find that in. Okay, and that is the specific heat. M is mass, okay? And mass is generally going to be found in grams for this sort of stuff. So if it's not in grams, switch it to grams. Okay, and then finally, the delta T. Delta just means change, okay? And T means temperature. So delta T is just the change in temperature. So you look at your initial temperature minus your final temperature, okay? So let's go ahead and do a problem with this, all right? Does anybody have any questions so far? No.
The delta T, did you say it was the initial temperature minus the final?
Final minus initial. Final minus initial is generally what you do. Okay. Yeah. So anyway, it'll make a little more sense when we do a problem here. So is anybody taking notes, or can I clear this to do the problem? Okay.
1 second.
Okay. Let me know when you're good, and I'll be moving on.
Yep, I'm good.
Okay. All right. So let's go ahead and I'm going to read this off. So, in the construction of bridges and skyscrapers, gaps must be left between adjoining steel beams to allow for the expansion and contraction of metal due to heating and cooling. The temperature of the sample of iron with a mass of 10 grams, okay, so we know our mass equals 10 grams, okay, changed from 50.4, okay, so we know our temperature initial, okay, is going to be equal to 50.4 degrees Celsius, okay, and our temperature final is going to be equal to 25.0 degrees Celsius, all right, and this reaction, when it drops that number of degrees, it is going to release, okay? So the energy released is going to be 114 joules, okay? So we need to figure out what is the specific heat of iron, okay? So we just need to plug this all in, right? And so essentially what we need to do, and with this, I know Carly, I think, asked, generally just take the higher number, subtract by the lower number, okay? But generally you're going to do initial minus final, okay? So Ti minus Tf equals delta T, okay? And so what we're going to have is 50.4 minus 25.0. All right, and so that'll just equal our delta T is going to be 25.4 degrees Celsius for delta T. Okay, for the change, so the change is 25.4 degrees Celsius, which is a pretty big jump. So now what we got to do is plug and chug. And again, there's two ways you can do this, because again, it's Q equals C times M times delta T. Okay, and so you can plug those in right now and start solving for it, but if it were me, I would probably just kind of set it up. So I know that essentially I need to isolate C by itself. We're looking for the specific heat. And so what I would do is just take M times delta T and divide it over to the other side. So you're going to have Q divided by M times delta T equals C, okay? And so right now we've got it set up for this. And all you have to do is plug those things in. So C is going to be equal to Q, which is 114, divided by 10.0 times 25.4, all right? So when we have all of those, you put it in your calculator, handy dandy calculator. 10 times 25.4. You're going to have 200, so you'll have essentially 114 divided by 254. And yes, I did do 254 or 10 times 25.4 in my calculator because my brain is not working currently, even though that's obviously only 254. So then you're going to have 114 divided by 254. Okay, and then remember, this only can have 3 sig figs, so this should come out to be 0.449 joules per gram. Joules per gram times Celsius, degrees Celsius. Okay? Does anybody have any questions about that? Or are we all okay there? It's a relatively self-explanatory process again. And this is similar a lot to like what physics is. Once you know what equation you're going to use, you just plug and chug. And so now once we know, like we have up here, we know mass, we know our initial and final temperatures, we have our energy released. What do we need to find? We need to find the specific heat. Okay, we get it, we isolate C, and then we solve for C. Okay, pretty simple math stuff once you know, again, that kind of basic algebra. All right. So if there's no more questions, am I good to erase this stuff?
Lay down, right now.
Cam, do you want to mute yourself?
Lay down.
All right. So no more questions? Again, you don't have to mute yourself if you have questions, but I don't need to hear that your dog needs to lay down. All right. We'll erase this then. Okay. The next thing we're going to talk about is essentially a little bit more heat stuff, and we're going to look at another way that you can solve for heat, okay? But it's just going to be it's essentially using the same equation. I'm just going to have you guys do it a little bit differently. But one thing I want to talk about is what a calorimeter is and kind of what calorimetry is. So a calorimeter. Okay, so a calorimeter is an insulated device used for measuring the amount of heat absorbed or released during a chemical or physical process. Okay, and if you guys go to like a college and have to take chemistry, you will definitely do some calorimetry and specific heat labs. And essentially it's, I mean, we used like a styrofoam cup. I would have done something like this if we had the stuff. This year, towards the end of the year, I would have had to look and make exact sure, but it's kind of a cool process to look at all this. But yeah, I mean, so it's like an example they use is suppose you put 25 grams of water into a foam cup calorimeter and find that the initial temperature is 25.6 degrees Celsius. Then you heat up a 50-gram sample of an unknown metal to 115 degrees Celsius and put the metal sample in the water. The heat will flow from that hot metal to the cooler water. The temperature of the water rises. And that it essentially, the transfer of heat will only stop when the water and the metal are the same temperature. And so it's kind of something cool to watch there. But anyway, so let's kind of look at that again. And this will be some of the last stuff that we will kind of go over today. So if we have a piece of metal with a mass of 4.68 grams, absorbs 25 or 256 joules of heat when its temperature increases 182 degrees Celsius. Okay. What is the specific heat of the metal? And then you have to look at, could this be, could the metal be one of the alkaline earth metals listed in table 2? So this is one way that you can test unknown metals. All metals have different specific heats. So if you're unsure what you have, you would look at this. So again, we know that our mass, right? Mass is going to be equal to 4.68 grams. Okay. We know that our Q, our energy, is going to be 256 joules is the amount of heat absorbed. And then lovely for us, it already says that the temperature increased 182 degrees, so we know that our delta T, we don't have to do any work there. Our delta T is 182 degrees Celsius. Okay, so we just need to find the specific heat. And then we need to kind of determine what this could be. So, looking at this, we'll go ahead and put it back into that equation that we had before, where we isolated C. Okay, so C is going to be equal to Q divided by M times delta T. All right, and so you'll plug that in, and so you'll have 256 divided by 4.68 times 182. Okay, and this one is definitely not one that I can just do in my head. So 4.68 times 182. Okay, when you do 4.68 times 182, when you use sig figs, this will essentially go ahead and equal 256 divided by 852. All right, so we have 256 divided by 852. You should get that this is going to be equal to 0.300 joules per gram times degrees Celsius. Okay, so our specific heat is 3.00 or 0.300. Okay, and it asks, could this be one of the metals? Now, for the three of you who don't have a book, you can look up, because you'll have two problems that'll be like this. All right, and so you'll just have to look up specific heat of metals. But for everybody else, if you flip back to page, okay, so on page 520 in your book, you can look at table 2. All right, and this shows specific heat of metals. And so if we look, man, I see one strontium's, okay, on that table. Strontium has a specific heat of 0.301. So I can probably assume that there's just some sort of mathematical rounding thing up here. These are probably the same thing, so I can say unknown metal is strontium. Okay? And so that's how one way that you can use calorimetry and specific heat to figure out what metals you don't necessarily know. Okay? And to basically to figure out unknown metals. Does anybody have any questions about this? Okay, if nobody has any questions, this is the homework for next time. Okay, on page 4 or 521, I want you to do number 6. Okay, then on 528 or 525, do numbers 12 and 13. Okay, so those 3 problems, essentially it's 6, 12, and 13. All right, and again for Joe, Kyler, and Anthony, I'll type out those problems and send them to you in an email. All righty, but does anybody have any questions?
No.
All right, is anybody writing this down? Cam, are you writing this down?
I'm good.
Okay, I'm gonna go ahead and stop sharing then.